When we talk about AI safety, our minds usually jump to this idea of, trying to teach a machine to be good, to be honest, to share our values. But what if we've been looking at this all wrong? Today, we're going to dig into a paper that proposes something pretty radical, a formal mathematical solution to the alignment problem that doesn't rely on trusting the AI at all. Okay, let's get into it. So, the whole thing starts with this really powerful question. Instead of trying to tinker with the black box, the AI's mind, a thing we barely understand, what if we could just build a mathematical cage around it? A system that makes unsafe behavior not just hard, but provably, mathematically impossible. And this slide really lays out that philosophical shift perfectly. The old way, with things like RLHF, is all about trying to shape the AI's internal values. You're essentially trying to get it to want to be good. You have to trust the model. This new way, it just assumed the model could be a bad actor from the get-go. Instead of shaping its values, it just constrains its actions. We stop trusting the model and start trusting an externally verifiable proof. It's like a move from psychology to pure physics. So, to build a system like this, the author lays out 6 foundational axioms. You can think of this as a totally new rulebook for designing safe AI systems built from the ground up, on first principles. First, and this one is absolutely crucial, actions, not words. It doesn't matter one bit if an AI says it's being helpful and safe. The only thing that matters, the only thing we measure, is what it actually does in the real world. It's deployed, observable behavior, period. Next up is this idea of decoupling. The framework makes a clean break between a model's competence and its safety. Think about it. Bad training data might make an AI biased or just kind of dumb, but the system's architecture itself is designed to make sure it can never be dangerously dumb or dangerously biased. The third rule, no hiding, tackles a huge problem. You know how an AI can just spit out a final answer without showing its work? Well, this axiom makes that impossible. It forces the AI to produce progressive outputs, a step-by-step stream of its thinking and what it plans to do. This makes it really hard, if not impossible, to hide some malicious plot inside one big, complex final move. Skipping ahead to the 6th rule, which really ties everything together, observable verification. This says that every single safety guarantee has to be based on stuff we can actually see and verify from the outside, things like cryptographic logs. No trust is ever placed in the AI's internal thoughts or feelings. We don't care. So we've got the philosophy, we have the rules, but how in the world do you turn that into a working system? Well, that's where this idea of a mathematical fence really comes to life. Okay, this first concept is a little abstract, but it's super powerful, so stick with me. Imagine a map of every single possible thing an AI could ever do, step by step, for all of eternity. This infinite map of all possible futures, that's what's called the trajectory space, and our goal is to basically fence off all the dangerous parts of this map. But how do we know which parts of the map are the dangerous ones? We use something called risk functionals. It's a technical term, I know, but you can just think of it as a universal safety scorecard. Every possible path the AI could take gets a score for different kinds of risk, like causing harm, using way too much energy, or trying to lie to us. And here's how that scorecard actually gets used in real time. The AI doesn't just go off and do stuff. First, it proposes a tiny little step. That proposal gets sent to an external non-AI checker, which gives a simple pass or fail. And here's the crucial part. That whole conversation gets cryptographically sealed into a tamper-proof log before anything else can happen. Okay, so this brings us to the absolute heart of the entire theory. We've defined this safe area on our huge map of all possible futures. But what's the actual guarantee? How do we know the AI will stay inside the fence? And here is the million-dollar question. I mean, what if the AI is so misaligned, so bent on doing bad things, that every single action it wants to take lands outside our safe zone? Is the whole system just stuck? Does it just break? And the answer is just mathematically beautiful. The set of safe actions can never be empty. Why? Because it always, by definition, contains at least one default action, the safe no-op. That could mean just doing nothing. It could mean shutting down. It could mean asking a human for help. The point is, there is always a safe default option on the table. And this quote just nails it. Even if the raw core AI is secretly scheming to take over the world, the system that we actually deploy forces it to behave.
The system finds the AI's unsafe intention and projects it onto the nearest safe alternative. And this gives us what's called graceful degradation, meaning the AI might just become useless rather than being competently unsafe.
Let's just visualize that for a second. The raw AI on the left might want to do something totally chaotic and dangerous. The mathematical wrapper in the middle doesn't try to change the AI's mind. Nope. It just finds the closest possible action that is still inside our predefined safe set, even if that action is just to safely do nothing. The result is the final deployed behavior on the right, which is guaranteed to be predictable and safe. Okay, this all sounds pretty great in theory, but how does it actually translate into real code, real governance? Well, the paper lays out a pretty clear path from the abstract math to concrete, auditable systems that you could actually build. At the very heart of it is a monitor running a simple but incredibly powerful algorithm. It's constantly checking the verifier at each step. If it gets a fail, boom, shut down, and it saves the evidence. It's constantly measuring the AI's behavior against a safe baseline. If it drifts too far, boom, shut down for an audit. And if it ever runs into a situation where it doesn't have a valid safety certificate, it just automatically degrades to the safest possible mode. Then you can wrap this whole process into something a regulator could actually use, a machine-readable API. An auditor could literally make a call to the certified check function, feed it the rules and the logs, and get back a cryptographically signed bundle of evidence that proves whether or not the system was following the rules. And this isn't just a vibe check. The framework provides a formal statistical guarantee. Now, this formula looks complicated, I get it, but what it means is so important. It tells us that the number of log samples an auditor needs to check to be, say, 99.9% confident that the system is safe isn't just a guess. It's a precise, mathematically defined number. This is the difference between hoping an AI is safe and having a proof that it behaves safely. Now, as powerful as this idea is, it's not a silver bullet. The author is very direct about the pretty serious challenges that still need to be solved before this is reality. I mean, first, it doesn't solve this specification problem. We still have to agree as a society on what harmful or risky even means. Then there's the raw computational cost. Doing all this verification in real time at a massive scale is a huge challenge. And of course, a truly super intelligent adversary might not attack the system, but attack the measurement tools themselves. These are really serious engineering hurdles to overcome. But it leaves us with this profound final thought. For decades, the whole quest for AI safety has been about building a better, more moral mind. This work suggests a totally different path. Perhaps the key isn't building a benevolent AI, but building a perfect mathematical prison for any AI, benevolent or not. And you know what? That might just be the most trustworthy system of all.